Good evening. Good evening, everyone. My name is Brad Laidwick, and I work here at Imperial College. I'm a lecturer in the Department of Chemical Engineering, and it is my pleasure to welcome you all here this evening for this public lecture. As you might guess, it has an Australian flavour this evening. I'm an Australian working here at Imperial College. Our guest speaker for this evening, who's seated on your left over there, is Matthew Hill from CSIRO in Australia. And our compere, our moderator, is Adam Hills, a well-known comedian and TV presenter who's also Australian. The science, however, and the breakthroughs and the innovation and the exciting stuff that we're going to hear about tonight is absolutely global. It's absolutely world-class, and it is critically important to the world. So I won't say anything more about what's happening this evening other than to say welcome. On behalf of Imperial College, we are absolutely thrilled to see you all here. It is a full house. We were oversubscribed for the event, so you people are the lucky ones. You are the ones here in the room, seeing it live and with the opportunity to ask questions at the end. But there are an untold number of people watching this streamed live on the internet. Potentially 6 billion. Likely less. Either way, it is a magnificent event. We are absolutely overwhelmed with the response. When we put it together, it was mostly initiated by CSIRO with the terrific support of the Australian High Commission here in London. We were not sure of the response that we got, and it was absolutely overwhelming. So thank you for coming. Have a wonderful evening. Enjoy the talk, and most of all, get involved. This will be an interactive event. You'll have the chance to ask your questions, to give your opinions, to basically be a part of this event. Not just a passive recipient, but an active participant. So enjoy the evening, and thank you for coming. Let me introduce your moderator, your QC, Mr. Adam Hills.
Thank you. Hello. Hello. My two jobs here have just been done, which one was to get some laughs, tick. The other was to get used to the Australian accent, and that's already been done. So it does really sound, I've got to say, sounds so weird hearing an Australian accent talking about scientific achievement around the world. Do you know what I mean? It really, for me, even having spent time in London, that just sounded like the crocodile hunter getting excited about science. Oh, we've got some great innovations. So clearly, just get used to hearing Australians. And I'm honoured to be here tonight and introducing Dr. Matthew Hill, because most people in England don't realise Australians have scientists. So it's nice for me to say we've got one. I mean, you all know we're great at sport, rugby, cricket. To get used to the Australian accent, I suggest you just imagine the convict Cockney accent slowed down because of the heat. And you've pretty much got the Australian accent. 200 years ago, convicts got off ships just going, bloody hell, that was a long bloody journey, 3 bloody weeks on the other side of the bloody planet, where are we now? I don't know, but it's a bit fucking hot. And the Australian accent was born. The CSIRO, by the way, for those of you who don't know, that's one of those, if you're an Australian and you know the letters CSIRO, that's kind of the pinnacle of scientific achievement in Australia. It's one of those iconic places that we all look up to. I didn't know this until I was given these facts. The CSIRO in Australia invented Wi-Fi. Oh yeah, and you're all nodding. It's like, I'm the only guy in the room that didn't know that. That was great, just watching you all go, yeah, we knew that, dickhead. My favourite fact is this: the CSIRO, not just the fact, the way it was presented to me, the CSIRO invented the insect repellent Aerogard to help keep flies off cattle and used it on the Queen in 1963. Is exactly the way Australians work. And of course, CSIRO collaborates with Imperial College here in London. And the man sitting over here is one of Australia's leaders in the field of science and innovation. He's an Australian Research Council Future Fellow, the winner of a 2014 Australian Prime Minister's Prize for Science. Matthew, I'm going to read this off the page. He leads an interdisciplinary team of researchers that are actively involved with industry partners to bring exciting discoveries in the laboratory to market. I have no idea what any of that means, but it sounds amazing. He's developed a platform technology position in a group of materials known as metal. You know what you're here for. I don't know why I'm describing this. There will be questions afterwards, and please, I've got some questions to ask that I've been given. Please don't make me go to them, because clearly you know way more than I do. I've also been told by Matthew that there are some people here who probably know more than him and are looking to give him a grilling, and there are some people here who don't really know that much and will have some pretty simple questions. And I want to mix them up and make sure at the end everyone gets a go. So if you're massively smart and probably smarter than Matthew, let me know so I can call on you for some really smart questions. Okay. If you've no idea what's going on and are going to make a fool of yourself, put your hand up as well. Most of you, excellent. Okay, that's good to know. Right, but like I say, please don't make it awkward afterwards. If you have a question that you think of, run with it. Otherwise, I'm just going to talk to him about the Rugby World Cup for 15 minutes at the end. Ladies and gentlemen, it's my pleasure to present to you Dr. Matthew Hill.
Thanks, mate. Thanks very much, everyone, for coming tonight. It's a real pleasure to be here all the way from Australia, and my namesake here. We've got the same accent, the same name. We don't support the same football team, unfortunately. We should probably do a bit better in that regard. But I'm from the CSIRO. We're part of the public service in Australia, and I'm here to tell you about how when I go to work, I make a whole lot of nothing, which is about right for an Australian public servant, if you might think about it. Pretty busy there, not to do any stereotypes. So if we just move on to my first slide, that would probably get things moved along. Problem?
No, I think so.
Oh, is it through here?
Yeah.
Okay, thanks for that. As you can see, I'm a bit of a Seinfeld fan as well. So here's where I grew up, which is Sydney, Australia, and the University of New South Wales, where I did my PhD in chemistry, which took a lot of focus, to be honest, because look what's across the road, Randwick Racecourse. We actually used to do our exams at the racecourse and watch the horses go round. So just to get a degree in that environment is pretty good. Coogee Beach, if you're not familiar with that, that's the one next door to Bondi Beach. We used to have people sitting in our lab with a nice webcam of Coogee Beach, and as soon as any form of surf broke, the lab got very empty. So it's a tribute to me to have actually got a degree when I was there. And after I finished my degree, I moved down to Melbourne, the southern tip of Australia there, and I worked at the CSIRO, Australia's national laboratories. And we're situated in probably what's the centre of science in terms of chemistry and engineering in Australia, out next to Monash University, which is our biggest uni. We've got the Australian synchrotron. For those who don't know what a synchrotron, it's basically a really, really bright source of light, and you can shine that light into your samples that you've made to understand what they're made of and how they're put together. And so we've got one right across the road, the big circle building there. And we've also got the Melbourne Centre for Nanofabrication, which can be used for making cool devices as well. So it's a really good spot to do innovation in Australia. So that's a pretty nice vista. And I thought while I was showing some nice vistas, I'd just show one more. I was in Paris when this happened, and I never realised that French people are actually Australian, because they were all cheering for Australia. So that was really quite interesting, but probably enough rubbing that one in. To be honest, I'm not really a rugby fan until Saturday night. I really became a rugby fan, so that was good. So a bit about CSIRO, as we call it, because it is a bit of a mouthful. So just for those who don't know what it stands for Commonwealth Scientific and Industrial Research Organisation. So basically what that means is that we're halfway between a company and a university. So something cool gets discovered in the lab at a university, but it's not ready for a company to take on, and our job is to sit in the middle there and do our best to help things come across. And the other part that we do is to focus on the areas that are of national priority for the country. So some of those areas that are shown here, if you think about Australia, these probably come up pretty quickly. Minerals, yes, we have quite a few of them. Agriculture is a real foundation stone in our country. And growing areas in digital productivity and services. We're actually pretty good in that area. We did invent Wi-Fi, as Adam mentioned. There's a proud history there. And what I'm talking about today sits under manufacturing. So really what I think about here is we've got all these natural resources in Australia. We're very good at, we can send iron ore to people, but wouldn't it be good if we could send something that was much more value added? So we're looking at, can you take these raw materials and turn them into something that has really high-end use? So we've talked about a couple of these good inventions, Wi-Fi and the AeroGuard, which was a good one. When the Queen was coming, we thought we'd better keep the flies off her. A couple of other ones that probably reasonably Australian, the total wellbeing diet. We're not the skinniest people in the world, so CSIRO put out a book and said to everyone, you should probably eat this. And it's been a bestseller for many years. Polymer banknotes, so that's plastic money. So when people like me forget to take all their money out of their clothes and chuck them in the wash, you can actually use it again. And also you can't counterfeit it, so it's pretty cool technology. Extended wear contacts. Maybe us Aussies aren't the most busy people. You can leave your contacts in. You don't have to take them out every night. And that was discovered at the CSIRO. So anyone who wears contacts that you can leave in for weeks at a time, that's where it was discovered, actually across the road from me. And just one for all the professors in the audience, atomic absorption spectroscopy was actually discovered at CSIRO as well, quite a while back now, by someone who didn't have a PhD, heaven forbid, who discovered that one. So we've talked a bit about Australia coming first. We like coming first, we're pretty competitive. Unfortunately, we picked the wrong area to come first in, which is how much carbon dioxide do we emit per person. I guess it makes a lot of sense when you think it's a huge country with not many people in it, and almost all the electricity that we use is from burning coal. So we have a huge problem in Australia that we're emitting a lot of carbon dioxide, and we really need to be leading the world in addressing this challenge. And of course, Imperial College, for those of you who don't know, walk right past here, are working on this exact area. That demonstrator unit that's just outside is a great example of capturing carbon dioxide and stopping it getting into the atmosphere. So I'm going to talk a little bit, and I might sound like I've got a bit of a lisp tonight. I'm going to talk about some materials called metal organic frameworks, or MOFs. And what they are is they're a powder that has some remarkable properties. So they have more internal surface area to them than any other material that's ever been discovered. And in fact, if you had a teaspoon of material, you'd have the same amount of surfaces inside that material that an entire football field would have. And to be honest, I don't quite get my head around that still. It's really quite remarkable. And what they actually are is they're kind of like a building scaffold. So you take a metal atom, and it can be just about any metal atom, or maybe a group of a few of them together, and some kind of organic linker molecule. And you can build them together and make the struts that we show there on the right-hand side. And basically, one example of that is that the metal could be zinc or zinc oxide, so that's sunscreen. The organic part can be a molecule called terephthalic acid, which is what we use to make Coke bottles. So sunscreen plus Coke bottles, and you can make one of these materials that has more surface area than a football field in a teaspoon. So they're really quite remarkable materials. So what I'm going to talk about tonight is taking advantage of this structure. So one thing is you've got all this surface, all these internal holes. It's like a sponge. So if you think about a sponge in your kitchen, it's got lots of holes. You can soak up water into the sponge. If you had more and more and more holes, you could probably soak up more and more and more water. And that's what we can do here. We can soak things into them. And the other thing is that the holes are all the same size. So you could also use it like a sieve, and you could separate big things from small things, like you might do with, say, flour or something in your kitchen. And so basically, I'm just going to show you a couple of things that we did, some on purpose, some not on purpose, like all fun research, and that contributed to stopping carbon dioxide getting into the atmosphere. So I like to start with the most important bit, which is that we think rugby is a team sport, science is a team sport. I hardly did any of the work in this presentation. I might have sat in my office and said, hey, do you reckon you should try that? That might be fun, or gee, that's interesting. But these are the guys who did all of the work. And just an example of how CSIRO is a bit different to a university, we've probably got someone in this team from every department of a university. So we've got engineers, mathematicians, chemists, physicists, biologists. And so we have a lot of language translation issues, not because we're from different countries, but because we're from different disciplines, and what someone means in one language doesn't work in another one. And basically we all come together because we're interested in materials with lots and lots of holes in them, and putting things in the holes and releasing them. And these are all the different applications, but I won't talk about all of them because it might give us all a bit of a headache. So also being a bit parochial, I would just like to point out that these materials are actually discovered in Australia. This is Professor Richard Robson, and for the Australians in the audience, that's Naomi Robson's dad. So she's a famous host of one of the tabloid TV shows, and her dad is one of the most prominent professors in the world. And if you just have a look here, he published a paper in 1989, so this was the first material, and he basically said, these things look really interesting, you can link them together, and as pretty simple ingredients are going to give you big holes, and maybe you could use those holes to do lots of things. So a very long time ago, Richard was right on to what might be the potential for these materials. So a lot of people say, oh, how do you make them? And so usually I say with a bit of a headache once we get going. You're kind of trying to do two different things. So if you're a chemist, you often do chemistry that's called coordination chemistry. So this is about geometry. You're kind of trying to line up things in the right angles together. And in chemical engineering, often we do what's called polymer chemistry. So this is doing the same reaction again and again and again. And when you're making MOFs, because they've got the coordination part and the polymer part, you have to do both at the same time. And so basically, it can take a long time to work out how to make one of these materials, but once you've got it, it can be reasonably easy to continue with it. So this is a very high-tech video that we filmed in my labs using iPhones clamped to a bench, but it did the job pretty well. So instead of lots of graphs, I'm going to show you some examples of what you can do with MOFs. Is there a way to turn this down a bit? Don't need to listen to the music in the background too much. This is our lab in Melbourne, and unfortunately, because a Victorian put this together, that's an Australian rules football field that has the surface area of a teaspoon there. There's the CSIRO logo. In good tradition, Australia behind bars, of course, that's what it looks like. And as someone who came here, or whose ancestors came to Australia against their will a few hundred years ago, that's always good. So I mentioned using them like a sponge to soak up water. Well, here we're soaking up carbon dioxide. So we filled this balloon up. There's a little bit of powder in the bottom, and what's happening is the carbon dioxide molecules want to go inside that powder. And so we can empty an entire balloon into just a tiny amount of powder. So imagine what you could do if you had lots of it. So if you can do that for a gas, maybe for stopping carbon dioxide getting into the air, you can do it in a liquid too. And here we're just capturing a bit of food dye actually, but you can imagine in water that could be a pesticide or maybe some lead or something that you don't want in the environment. We can soak that up as well. And when we started doing this, people said, yeah, but how do you get it back once you've captured it? So we made them magnetic. So you can throw them into a pond. Maybe you've got to get a boat with a magnet on the bottom of it, and you can pick them up and stop them being left in the pond, which is probably a pretty bad idea. So those are all examples of using the material like a sponge, where there's lots and lots of holes to soak something into it. The last example I want to show you here is using them like a sieve. So all the holes are the same size. You can just make a thin layer. It looks like a piece of plastic, like a piece of Coke bottle, and one gas wants to go through and another one doesn't. So you just need a small amount of material and you can get a lot of purification. So here we're separating methane from CO2. That's how we make clean natural gas. This happens all around the world. And we found that when we get the right composition in the right MOF and the right polymer, we get really, really cool separations. So this is our first graph for the evening, and I just want to go through what this is showing us. This is a graph of that balloon being emptied into the powder. So what we do is we connect the material up to a vacuum, which takes us down to a pressure of 0. And then we start putting in carbon dioxide and we see how much gets soaked up by the material as we go up. So this is just going up in pressure. And this was an example of some materials we made where we were able to change how much went in. And you can see we can get that's 150 mils in 1 gram. So if you think of a soft drink can, this is about half a soft drink can of gas in 1 gram of material. So it really can soak up huge amounts of material, huge amounts of carbon dioxide. So there's a lot of people doing research, and people here as well. Or maybe you could make lots and lots of this powder, and you could connect it to a coal-fired power station, and coming out the spout is lots of carbon dioxide, and maybe you could capture it with a material like this and stop it getting into the atmosphere. So that was one of the first things we did in this area. And whenever I talked about that, people would always say to me, well, how do you get it out? And a lot of the research in this area is on getting material, the CO2 out of whatever you've caught it in, because you want to reuse that material. You can't just throw it out and you take the CO2 away. Hopefully we turn it into a product rather than putting it in the ground, but that's an area of ongoing research. So we started thinking about, well, because you can make these materials out of just about anything, maybe you could engineer them so that they want to release what's ever captured inside. Because right now what we do is we generally use temperature or maybe a vacuum to get out what we've captured, and that can use quite a lot of energy to do that. And we were thinking, especially back home, is that we've got a lot of UV invisible light called sunlight, and maybe we could use that instead to actually release what we caught inside. And so here's an example, and just a warning for any students in the audience, don't do too well at your research, because you'll be forced to go and wring out a sponge and get a photo of it taken. And that was my student Rochelle. She was taken outside and told to wring a sponge. She didn't think she'd be doing that day, but what she did was made one of these structures where the organic parts, the plastic parts, were made of molecules that we know change shape when you put sunlight on them. So then we filled up the sponge with lots of carbon dioxide in the dark, and then we put concentrated sunlight onto it, and we found all the gas molecules coming out. And what that looks like in a graph is here. So Rochelle went away, and first measurement she did was the control measurement, which was the one in red. So again, we're going up in pressure and we're saying how much goes in. So this one isn't up at 150, but it's still a pretty good run. And then she connected up her sunlight to the powder, and we saw a lot less went in. And then we did this, we turned the light on and off, and we could see we could make the gas go in and go out. And then when we looked at it for if we just used broad sunlight or we used the most efficient wavelength of the sunlight that was absorbed the strongest by the material, we could get almost all of the carbon dioxide out of the material using sunlight. So it's a nice alternative way of doing this. So basically we've got a sponge that wrings itself out. Was that discovery, which was pretty fun. So that one we did, and you'll see one of the authors here is Brad. Brad and I used to sit in the same building, but it's a bit longer commute these days. And that was a really fun piece of work for us. But then we got another student to get together, and he was saying to us, yeah, but how much of the material are you going to need on a power station? And so he did some back of the envelope calculations on this, and he came up with 146 tonnes of material for every power station, which is a lot. And if you went and bought that from BASF today, just out of their catalogue, well, that's a lot of money. So that's 2.9 billion Australian dollars, which is about 300 pounds UK at the moment. And but if you, instead of making a big lot of powder, you put it in a thin layer of material and you make what we call a membrane, and you get the composition of that just right, well, now you only need a few hundred kilograms of the material. So that's a different ball game. And membranes have been very attractive in this area for a long time. And some of the top membrane researchers are at this university actually, and would be working on this as well, because we know we need less material and it's more efficient to do the separations. So we thought, well, let's just start throwing some of these MOF powders into some polymers and see what happens. And we were starting to get some sort of good results, and that was okay. And then, like all fun discoveries, we did something that was completely by accident. We weren't trying to do this one. And people say, oh, do you have a eureka moment? And I say, oh, not really. We had a that's weird moment. We weren't expecting to do something. So in the membrane game, there's been some polymers that are well commercialised for a long time. And there's a huge research community, lots and lots of new polymers, but not, even though they look great in a publication, sometimes they don't make it to the next stage. And one of the reasons for that is that they're not so stable. So if you make a good polymer, they have lots of holes inside them, and those holes are where your CO2 can go through and your other gases like nitrogen that's in the air don't go through, and you can separate and stop it getting into the atmosphere. But over time, those holes tend to close up, the material collapses down on itself, and it stops working. So sadly, it's like a tantalising result sometimes, that the best materials just can't work for long enough to be used. And so we were just trying one of these materials, and we called it PAF1 in this case, and we put it in some polymer and formed, I guess the good analogy is it's kind of like reinforced steel. So the polymer went into the holes of the MOF that we put in there, and it sort of locked it in place. And so now we've shown with a whole bunch of different polymers that we can stop this aging happening and make the material last longer. So I'll show you what that means for one of these filters. So here we're looking at how fast does the gas go through versus how long have we been trying to put it through. And we just did this one as a percentage. So the dotted lines are our control material, and in this game you've always got to do control materials because it really changes lab to lab, and who did what, you can really change the performance of a material. So we always just say, well, in our lab we did the exact same thing, and all we did was change one thing, which is a good way to do science because then you can delineate what's going on. And we saw this nice red line here. So over 6 months, the same amount of carbon dioxide is going through as it did on the first day, rather than losing sort of 2/3 of its performance. So one of these polymers now lasts a lot longer than it did. And as Brad was saying, it's really a global occupation. This was done in Boulder, Colorado, which is a pretty good place to do some work. It's one of the more beautiful places in the world. And I remember we were doing the measurements, and we had a membrane that worked pretty well, and we put it away and did a few other things. And a week later we said, oh, I've just got to check it. And we went and put it back in, and it was still working. And we said, why is it still working? And so that led to 2-3 years of work trying to work out why, and trying to prove that it was a consistent thing. So sometimes the worst thing you can do is find something unusual, because then you have to do lots more work, but that's the fun part, right? And then the other nice part of it was that not only does it last longer, but it actually works better too. So the dotted line, this is just, instead of a percentage, the absolute numbers. So the dotted line is the speed here, the material on its own, and when we put our additive in, and we only have to put 5% in, so it's almost nothing, we get about it works 4 times faster. So that means maybe you can use less membrane, or you can deal with a bigger problem. But in carbon dioxide capture, there's a lot of it around, so we need to be going as fast as we can. So that led to us thinking, the eagle-eyed of you might have noticed that while the carbon dioxide stayed in place, the nitrogen sort of didn't quite. And in our mind, there's no such thing as a failure, there's always an opportunity. And so we thought, well, what if you had a separation where one gas just kept going through all the time and another one didn't so much? And so we looked here at hydrogen and nitrogen separation, and this is really important in things like making fertilisers, and hydrogen, of course, being a renewable energy molecule, it's becoming very important. And maybe Australia's starting to get back. We've actually built the biggest renewable hydrogen plant in the world. It's getting built right now in the northwest coast of Western Australia, because you need sunlight, space, and access to coastline. So those are a few things that we have quite a lot of down there. So maybe we should be working on those. And what happened is, here's a graph of how well a membrane works. And all you need to know is that if you had a good one, you'd be right up in the top right-hand corner here. And so we made one of these membranes, and as we waited, the membrane just went up and up towards that corner. So it actually got better and better the older that it was. And so we thought it was like a good bottle of Grange, nice bottle of red. This is the same vintage that brought down the New South Wales State Premier, who got sent this by a questionable figure. Didn't know that it got sent to him, so I just like to put that in because maybe I'm spiteful. So this slide, this is my Vietnam. This is the first time that I ever tried to make a significant amount of one of these framework materials. So I was working a few years ago in Berkeley, so over near San Francisco, and we had an interesting material that we'd made, and to finish off the work, we just needed to make like 2 grams of it, so sort of like a couple of teaspoons worth. And the only way that I could do it was to get lots and lots and lots of tiny little vessels and do the mixtures all at the same time and then combine them, and it was a real pain in the neck. You'd think, why don't you just get a big bucket, throw everything in, and your product comes out. But what goes on here is a thing called nucleation. So these MOF powders, they look like sugar cubes, salt cubes maybe, and they grow on the edge of the glass. So if you have a big bucket, you have less edge. So in this case, we just didn't get the material. And you can see here the reaction conditions. We had to wait 10 days to get this product to form. So when we publish this, and you might talk to a company and they say, oh, that's really interesting. Could we test some? Could we have like 50 kilos maybe, just a small amount, and we'll test it out? And, you know, that's bad news, right? So you sort of have to be very polite at that stage and say, thanks for asking, and so on. But we were thinking, how could you take advantage of this, all of the surface area being needed, but to scale it up? And so my background's chemistry, so I thought, wow, there's this new thing called continuous flow chemistry, and I went and talked to the chemical engineers who said, oh yeah, no, we've been doing that for about 30 years, but you know, thanks for coming to the party. But the idea here was that you could take, these are little coils, so instead of doing chemistry in a beaker, we can do it in a coil. And in my view, this is probably going to be the future of sort of all of the advanced materials production because it's so much quicker. And what we were able to do, and it was sort of all new when we did it then, was to do MOF chemistry in these coils. So what this is showing is here's a solution where we've dissolved our metal. So we might say take some copper salt, and we dissolve it in a solvent like water or an organic solvent, and we do the same with our plastic material. And then these are pumps here, so we can very carefully control how they mix and what conditions they meet each other, and then the material comes out as a suspension at the other end. And so we started testing this, and so remember I said 10 days for that other material. The fastest that we've ever made a MOF through one of these reactors is 1.2 minutes. So it's a totally different ball game for us now. And maybe people can ask me about why, and I can speculate a bit, or maybe they can tell me why later on. And so what we did to start was we just started small. We got a little baby lab instrument here, and we could get, in every hour, we could get 40 grams of material to form out of this one. So we thought that's pretty cool. And the reactor was 10 mils in size. That was the size of the coils there. And so then we got a bigger one, and it could go up to 100 mils. And sure enough, we got about 10 times as much material coming out every hour. So then we thought, right, let's get going. And I was having coffee with some guys who are minerals process engineers at CSIRO. Obviously, we have a few of those. And I said, I talked to them about this, and could you help me build a really, really big one? And they said, how big? And I described it to them, and they said, that's a really, really small one. Because they're used to 3-4 story size materials. But this is our reactor here. It's a 2-litre, 2,000 mil reactor. So we call it the Moffinator 2000. It can make up to 10 kilograms every hour we can get out of this. And it's like a flood when you turn it on. It just comes flying out the other end. So now we've got pool chlorine buckets sitting in the lab full of this stuff. So we've probably got the other problem of who would like some. We can send you some because we've made lots and lots of it. So actually we're probably going to start a company to start selling some materials in this area because this was a lot more successful than we thought. We were just trying to make enough that when a company knocked on our door, maybe we could give some to them. But it worked really fast. So just to finish off, I thought maybe I could do a bit of a compare and contrast from global science to what's going on in Australia right now. And to be honest, it is a very tough time in Australia. It's probably just as tough as it is in Europe to be a researcher. We're losing a lot of funding. It's not easy to be a scientist. And so we've really got to do whatever we can, probably work together as much as we can to get through this. So here's some figures that we can see. 1 billion cups of coffee, probably a fair percentage of them from this room. 26 billion hours of research being done. So what are we doing with all those hours? That's a lot of effort. And most countries are spending between, say, 1% and 4% of their budget on research and development. So that either sounds like a huge amount of money or a very small amount of money, depending on who you are. But either way, that's what it is. And we're producing almost 1 million papers a year at the moment. So that's a lot of publications going out there. How do we sift through all of that and work out what did we actually learn? Because at some point, there's only so much information that people can absorb. And here's a graph that the Australian chief scientists had commissioned, which was to look at what the cultures are like of companies in certain sectors that were identified engaging with scientists and using what they know to help make more products. And I guess we can see that most people are between 30 and 50%. Here's the UK, probably not doing so well. And here's Australia down at 4%. So well done, Australia, 4%. Even New Zealand's beating us. That's a big problem. So there's a lot of opinion about why that is in Australia. And some people say it's because there's been too many other opportunities. And yes, we never had a recession because we had other stable sectors moving along. But there's a lot of us who think this is the number one thing that we should be focusing on in Australian science, is to make that go up as high as possible. And I certainly spend a lot of energy in that area trying to increase that. So probably, if anyone wants to talk about that, I need to hear from you about what we can do in Australia, because we're behind the ball game. So one thing we thought about in Australia was these two pathways. So here's taking some fun idea that a student discovered on a Friday night in the lab and said, that's weird, to now it's on sale at Tesco for £19. So how do you do that pathway? And usually it's a pretty long and painful thing. So you've got the fundamental research, then we do a bit of applied stuff. We call it de-risking research. So this will be where we're trying to make it a bit safer for a company to take it on without losing too much money. And then you've got developing the product. So you've got iPhone 1, iPhone 2, so on sort of stuff. And right now we think we've got this in Australia. We've got the unis and the CSIRO doing a lot of overlap, but not necessarily doing anything together. And then we've got a bit of a gap. And then industry sitting over here saying, let me know when I can just buy something and I can put it on the shelf. And so that's a big problem. And so one thing that I tend to yell from the rooftops all the time is saying that we need to do this in Australia, and maybe I can hear from the audience about how it's happening here, is we need to cover that gap and then have porous borders where people are filtering in between all the organisations and helping that pathway to be strong. So I think that's about it from me for now. I want to thank everyone very much for your attention and putting up with too much talk about the rugby, although is there such a thing? I'm not sure. And it's over to you, so thanks everyone.
All right, I'm going to do that awkward thing and say, does anyone have a question? Okay, let's talk about the cricket. No, sorry, yes. There are two hands. I didn't see which one went first. You can both have a question.
Is this on? Okay. You had a slide at the beginning about the CSIRO structure, and one of them said biosecurity. Mm-hmm. I'm curious about what that is.
Well, it's probably a pretty broad area. We often joke in Australia that you could probably get on a plane with a machine gun and come to the country and that'd be fine, but if you had an apple in your pocket, you'd be in big trouble. Because we're so far away, we do not have many of the common diseases that are around the rest of the world, and we'd like to keep it that way. And so a lot of our research is done there is working out how to stop diseases coming in, and also when they do, how to stop them spreading. Yeah. So one nice example is some of our British friends brought a few rabbits over a few hundred years ago for a bit of sport, and there's quite a few rabbits in Australia now, like plague proportions of rabbits. And so CSIRO actually invented a virus to try to kill the rabbits, and it was highly successful, and was actually, it was actually a way to protect the environment because they were doing such damage. But that was the other side of biosecurity, is to stop local species being threatened.
And the other question over here, yeah.
I wanted to know, and you may not have any figures on this yet.
Hang on, Mike's coming.
Sorry.
There you go.
What are the costs like per tonne of CO2 sequestered? Because one of the big problems with CCS getting off the ground has been the cost being much higher than any of the carbon taxes worldwide. Do you have any figures of how much it would be likely to cost?
My stuff's a bit early. We tend to think about how much energy it costs, and I guess energy is another way of thinking of money. So some of these techniques are a half or a third as much energy, maybe, but that's only in small scale at the lab, and you've really got to build bigger instruments to find out. But certainly, there is now a full-scale demonstrator unit in Canada that's out there, so we know that in the right circumstances, these things can actually get out into the real world. Now the question is, will that happen before or after we stop burning coal? I think before. We're still doing it a lot, and we're increasing the amount that we're doing it in some countries. Yeah.
Hi. So I was wondering, when you absorb molecules within the MOF frameworks, to what extent do they expand, and how does that affect the structure of those materials?
So typically they actually don't expand because they're a ordered structure. They've got all these surfaces that things can stick to. So, there's some that do and some that don't, but as a general rule, we would say they actually don't expand. So probably the way to get your head around that is that they're 80% empty before we put something in them, so there's plenty of room to put something in.
Okay.
Back a few rows. Yeah, you got it.
So going back to the beginning of the process, the design, do you sort of throw things in there and you don't know what kind of geometries you're going to get back, or do you have a really good idea of the design, and then do you sort of send it to the synchrotron to see what the structure is?
Yeah, so I guess that depends on how honest we're being. One of my mates is quite a famous professor who's responsible for close to 10% of the known structures. And I said that to him one day, you must know exactly what you're going to get by now. And he said, oh, not really. He has a basic idea, like it won't be this or it won't be that, but he's surprised probably every day as well. So we also have a theoretical database, so you can, in a computer, put the pieces together like a jigsaw puzzle and work out what all the structures might be. And we've got one of those databases in our lab. There's about 100,000 structures in it. So often someone will come and say, oh, can you do this? And we have to start with that database to sort of find out. Yeah.
Thanks.
Hi. You mentioned that you can make MOFs from Coke bottles, basically, so from the PET or from the terephthalic acid. Mm-hmm. Do you think you could also use a bio-derived acid? I know Coke is looking into PEF. Could you also use the F?
Yeah, absolutely. So, one of the biggest problems with MOFs is they tend to be expensive, and we did a bit of a study on why they're expensive, and it's often because of the ingredients. So if you can get a bio-derived ingredient, and I think I sort of said at the start of the talk, we're trying to use Australia's natural resources to make materials like this. So that's one thing we're really trying to get done at the moment, is to start with sort of bio waste and turn it into something like that. I mean, we think pretty cool.
Yeah. Hi, thank you very much for the interesting talk. I was just wondering, so if the concept is to have them as a sort of CO2 sponge, which partners have you, or if any, have you discussed with using the CO2 on the other end, and are they interested in doing it on the same sort of scale that you'll be capturing it at?
Yeah, so usually when I speak to a partner, the first thing I do is sign a confidentiality agreement. So this is probably not the right spot to talk about who I'm talking to. I would say that what we tend to look for is not just money, but a relationship to work over a long period of time, because we know you can't just do something like that and then it's going to work. So CSIRO has worked with Boeing for 25 years on all the bits and pieces to go in planes, and some of the biggest success stories are just coming through now, but took 20 years. So that's what we look for when we work with a partner.
Yep.
Environmentally wise, how sustainable is it to mass produce those structures?
Yeah, it depends how you make them and what they're made from. So if you have to use, say, you could make it really bad. You could use a bad metal that's maybe toxic, an organic molecule that's toxic, and a solvent that's bad as well. So we know this. So as I said, there's 20,000 different known materials. So that narrows down which ones pretty quickly that we want to look at. There's no point making something out of arsenic and saying, oh, look, it's really good for some application because what you said is going to be a problem. So, yeah, we try to think of that before time.
I've got a quick question. What other things can it be used for?
So, just about anything you can think of your imagination that can be put in and put out, and that's what my students are always doing. So we've done putting anti-cancer drugs in there. I had a student who, her sister is an oncologist, and she identified a form of cancer that was hard to access. So what we did was put these MOFs like a coating around an optical fibre, and we talked about putting the sunlight to release things. So you can use light down the fibre to release the drug, and you can get the fibre into other parts of the body, like using a catheter. It's a different way of putting it in. So we've done that. We've done fertiliser materials. We've done all different gases. We've done pesticide molecules. So anything you don't want to get out or you do want to get out. But what often happens when I talk to a general audience is they come up with 4 or 5 ideas that I've never thought of, and I've been doing it for years. So I bet that'll happen too.
You mentioned a couple of times that there are things that you had questions that you wish people might be able to answer for you afterwards.
Yeah.
Would you like to ask those questions and see if anyone's got an answer?
Well, I guess we were talking about engaging with industry, and there's a great example out here of Imperial working with ABB, and if people have stories, maybe they'd like to share about what they look for in an industrial partner and how they get success out of it. There's, I think, where we're very closely aligned as two organisations.
No one?
Maybe
Okay.
after. Yeah.
Yeah, there is a drinks reception afterwards, so feel free to.
Then you can tell me, pontificate at will.
Yeah, sure.
It seems to me that these MOFs, the chemical composition of them, the metal side, the polymer side, must be quite critical to the application.
Absolutely.
So we haven't seen anything about whether you use copper or zinc or whatever metal and whatever polymer might be for whatever application there is. And there must be a lot of permutations there.
Absolutely.
Right.
Yeah.
So getting the right permutation to the right application is the challenge, right?
Totally. And so when we were thinking about how do you make lots of MOF, the first thing we thought of was whatever instrument we build better be able to make just about any MOF because of exactly that. Someone's going to find an awesome solution and it's not going to be the one that we thought of. So we need to have that versatility.
These are essentially molecular sieves, right?
Yeah, so for people familiar with molecular sieves or zeolites, these are the next generation, 10 times more surface area, for example.
Which is where I'm coming to, is the zeolite thing. The synthetic zeolites have been used by the petrochemical industry for decades.
That's right.
In terms of catalytic cracking to make what we all use. Number one polluter is petroleum.
Mm-hmm.
Is there a way of linking in with those people that might help with your particular line of research here, where you're actually absorbing the carbon dioxide, and then you were showing us slides as how you get it out again?
Yeah,
well, we want to get rid of it, really.
There's certainly a lot of lessons to learn. So I guess when researchers started going into this field, we knew a lot about what zeolites, how you could make them and how you could put them in layers. And when we started making these thin layers, we were saying, well, maybe we just do the same thing. And we did start to see that in a lot of cases it translated across. So the zeolite, it took many decades to commercialise that. And okay, MOFs are taking a while too, but hopefully it'll be a bit faster by learning from zeolites.
You may take a look at the natural zeolites. That Australia has a load of those as well.
Tons of them, yeah. So
well, millions of tons of them.
absolutely. Well, we've got lots of everything. Yeah, absolutely.
And rugby players.
Yeah.
You were talking about closing that gap between applied science and industry. And what are your views about intellectual property? Because I know that that's kind of an issue when you're trying to close that gap.
Yeah, it's a funny one. So, sometimes you end up arguing over who gets what slice of a pie that doesn't exist. So that can be a tough argument to have. I guess we just look for the win-win. So we want to make sure that we don't stop something getting out, but at the same time, we don't want to hurt our own staff. So we don't want them banned from working on their own success stories. And so when we talk with people, we just be upfront about that's how we're trying to do things. But certainly it's a discussion you need to have early to make sure you get the right relationship. Yeah.
And so what comes next for you as far as developing this technology?
So we're working with a lot of partners where, you know, we've got timelines about maybe we get prototypes that we can put out in the field and run them for a while and see how well they work and if they stack up economically. And those things are sort of happening in our lab and maybe in their lab a bit too. And so we just want to get through those, and then if it works, you know, then the next stage will be, well, maybe we can start producing them. Yeah.
Right. Yeah, down the front here.
Yeah, I had a question, Matthew. So, you know, I can see you make these MOFs, you've got that kit, and you can make a whole lot of them, 10 kilos,
Yep.
maybe 100 kilos, and you put them into a power station stack. Two questions. Do you need to clean the gas, or can the gas go straight into the MOFs, or will it foul it up? And second, once you've absorbed all the CO2 onto the MOF, how do you actually get it back off again?
Yeah, so ideally you don't have to clean the gas, but I think you do. You want to protect these materials. So there's things like sulfur and nitrogen oxides that are present, which are pretty corrosive. Sulfur oxide, you know, that's acid rain, for example. So that's a pretty bad thing to be going in there. But that's not impossible to remove. There's existing technology to do that. Getting it out, typically you could heat them up or you could put a vacuum on them. That takes a lot of energy. So we're looking at other ways of releasing them, making the material on demand trigger the release rather than having to make it come out, because that's probably one of the key things, is how much energy does it cost you to clean your material so you can use it again.
And there's another one over there.
Hi there, two quick questions. The first is a follow-up. Removal of the SOx and NOx I can see, but what about the presence of water vapor, which is going to be in flue gases, and what's the kind of hydrothermal stabilities of these compounds?
Yeah, for a while, you know, that could have been a real bullet in this technology, but some of my friends in America discovered some MOFs that when they're wet, they actually work better. So that's pretty cool. So that narrows down from that 20,000. That takes a few more out to which ones we might use as ones that when they're wet actually work better.
So it's still a bit hit and miss, and you have to kind of screen all these different compounds and see what their unique behaviour is really towards water.
Yeah, so ideally, you know, someone will make a discovery like that, an experiment, and say, oh, now we've learnt something more. And once we can understand the mechanism behind that, you can start to do things in a computer instead of in the lab. So it's a lot cheaper and a lot faster to start looking for, well, if that one does it, you know, what other ones might do that? And then you can identify a few and go and check that, in the lab that they actually do, and that your prediction was right.
Sure, okay. And my second question was, in moving from the kind of small-scale experiments in screw cap valves and a block heater towards the flow process, do the conditions kind of carry across pretty much same temperature, same concentration, or what kind of difference in conditions do you have to use usually?
Yeah, it's let's say it's plus or minus 20%. So usually it takes us a couple of weeks. We've made 25 different MOFs in our continuous flow reactor from 25 attempts, and the longest it took us to get one working was about a month. Some of them, the first one we did, I gave my student 40 options and said, try all these 40 and maybe one of them will work. And he came back and said, oh, 37 worked. And so that was actually a problem, because now we don't know which the best one is. So then we had to go through and work that out. But it seems pretty amenable to transferring from the lab.
Okay, thank you.
Matt, a lot of the people in the audience tonight are master's students and PhD students and a bunch of whole cross of different disciplines. If you wanted to give them one or two key tips on how to have a really exciting career in science or engineering or research or innovation, and especially in the field of, like, you know, solving the world's problems, making the world more sustainable, making the world a better place, what would be the number one or the top two things that you would recommend for people just kicking off their research career now?
Well, I mean, everyone here is smart and everyone's working hard, so that's the first thing. You don't get anywhere without that. One thing I've seen people do that are going well is they know all their friends and they know what all of them are doing and why they're doing it and what's good and what's bad about it, because pretty much whatever project you're working on now, you won't work on when you go out into the real world. So being a bit of an all-rounder is kind of important. So you can stay in a broad space of sustainability or renewable energy, but you'll always be varying. And if you go down a pipe too much, you might become the number one person in the world on one topic, which is great. But then if you want to work on something else, you might struggle a bit. So I'm certainly nowhere near the top of any of the fields that I'm in, but I'm in lots and lots of different fields, and I know enough to get myself in trouble, and that seems to have worked so far.
Well, if there are no more. Oh, yep. Hang on. There's one back there, and then we'll come to the front, and then we'll probably go for drinks.
You might have mentioned before, but you've mentioned mostly about gas phase separations and absorption. Is there potential in the liquid phase as well?
Yeah, that's a good question. So yeah, we did try that. We tried an example separation of separating water from alcohols. So that's important for things like making biofuels. So you've done it's basically fermentation. So we're working with a company called Manildra in Australia, who are the biggest producers of ethanol. And they've got different stages of their purification, and they call it beer for obvious reasons. And then the next one's called gin. And they wanted help getting from the beer to the gin. So we had a look with our membranes, and we got the same stability effect. So we actually, one of the best polymers, we made it last for a long period of time. So that was kind of exciting. So that was one example of a liquid.
So presumably you need to change the framework pore size for your for the various things that you're trying to separate.
Yeah, I guess two of the main knobs you're turning is the size of the holes and what the holes are made of, so that what's attracted into them or not attracted into them.
And one last thing, do you ever get metal leaching through any of this?
Yeah, so people will say, "Oh, how stable are the MOFs?" And some people will say, "Oh, they're very stable," but I'll say most of them are not stable. So again, but a fair chunk of them are stable where you don't get metal leaching. So again, when we think of all of the materials, which ones we're going to use, the ones that don't leach are pretty important, that are stable. Yeah.
And was there one more question in the front? Yeah.
So I have two questions. My first one is, how you said something about terephthalic acid or the zinc oxide. Yep. How do you spell that?
After have some drinks, there's a TEREPHTH.
Wait. Could you start again? TERE.
Just type in PET, which is for Coke bottles, and go from there. You'll find it.
Cool. And my second question is about the thing. You had that graph with the aging polymers and how when you say it ages and in terms of the structural change during each of those steps when it becomes less efficient, what actually changes?
So basically, you've got a thin layer with lots and lots of tiny holes inside, and you're squeezing on it with a gas on the other side. And over time, those holes, there's a saying, nature abhors a vacuum. So those holes start to fill up with bits of polymer. And so there's less holes, there's less ways that the gas can go through, so it goes through slower. And so we just found totally by accident that out of the 20,000 MOFs, we just happened to pick one that stopped this happening. And once we discovered it, we found 4 or 5 others that also do it, but also about 20 or 30 that don't. So that's what we do, is keep those holes open.
Wait, so the polymer that actually went in those spaces was from the material itself, or?
Yeah, so what we're making is a thin layer. It looks like a piece of Coke bottle, and that's the polymer. And then our powder, we stir it in to the polymer before we cast it as a layer. And so when you look at them, sometimes you can't even see the MOFs inside because they're so well spread out in the material. Yeah.
All right, well, and one final question that I've got here that I will ask. Is Australia leading the world in this field?
We're doing okay. So we
if there was a World Cup of MOFs,
we might be on the dais. So we have a big project, which was essentially, we said, let's just get everyone in Australia who makes MOFs and put them on the one project. And one good thing about Australia is that was only 20 people. So we got everyone together, and we've done some really cool stuff. And now what we've done is we've partnered up with the European version of that project, and we're working together. So it's really it's a global challenge, and that's the only way to go ahead. One of my bosses once said to me, it's got to be like a guerrilla movement. You've got to have, instead of big armies, lots of little cells all around the world, but working together in an efficient team. And so that's what we're really going for.
Yeah. All right. And you ended up with the microphone, so I'm assuming you're going to say something.
Yeah, did you have anything else?
No.
Yep, great. Look, I have the privilege of closing out tonight's event, And to do that, I thought I would thank all of the people and organisations involved in order of importance. So I'm going to start at the lowest level with people that gave money and time. And those people are represented by these banners at the back here. So some of them come from Imperial College. The Sustainable Gas Institute is here at Imperial, the Energy Futures Lab, the department in which we're meeting tonight, the Department of Chemical Engineering, and the college itself, especially through the AV teams and the publicity teams, and the many people that helped put this event together. Thank you to those. I wanted to thank, in particular, the Australian High Commission. They helped facilitate this event because it is like a multinational event, and they also contributed financially to help support us today. Thanks very much to the Australian High Commission, the representatives from the Australian government that are here, and God bless those Australian taxpayers still paying their tax back in Australia. Second, I'd like to thank our guests tonight, Adam Hills for moderating the event, for being up here from outside the scientific field but willing to jump in and help bridge that gap, okay, to make it a fun, interactive event, and Matt especially for speaking. But I don't think you would mind me at all saying, Matt, that the most important people that turned up tonight are all of you and all of the people watching from home. Because without you coming, it would be Matt talking to an empty room. And that means nothing, right? That doesn't get a message across, that doesn't start a conversation, that doesn't start a movement, that doesn't inspire people. But that's what we did tonight. So that has been terrific. I'd like you all to put your hands together for our speakers and for yourselves. So as Adam alluded to, and as you probably saw with the invitation, there's a drinks reception outside, replete with Australian wine. So I'd encourage you to all go out and have a wonderful evening. Take a moment to say hello to Matt, ask him the questions that you were too embarrassed to ask here in the forum. Get to know someone that's here tonight that you don't already know. That is your challenge. Please do that. And most of all, go home safely after you've made the most of all the booze. So thanks very much for coming, and we look forward to seeing you at more events here at Imperial College. Thanks very much.
Thanks, everyone.